Right, good morning everyone. Our project is a random type. It's called Columbus. In our group it's William, Julie, Trim and me. Okay, this is our robot. It has a neck. We use the motor B as a neck for the ultrasonic sensor, more about that in a bit. It has a light sensor at the bottom to detect table edges and stuff, so it won't fall off table edges. It uses motor C and A as for the differential pilot. It has a sound sensor at the back, which we've had a little bit of problems with, and an XT brake, which is at the top. Evolution of the robot. Basically, when we were brainstorming ideas, we wanted our robot to mimic animal behavior. So mainly one important thing we considered was it has a turning head, so we can look around first before it turns the rest of the body. So we decided to move the whole robot around and put the motor B on the top. And this gave us a little bit of problems, but we kind of figured it out at the end. Use of tracks here. We know you're skeptical about tracks, but there are good reasons for using it. It has a zero turn radius. In tight spots, it's very easy to turn, and you can just turn on the spot by turning one track back and the other one forward. So you can just get around tight corners. And it was really helpful when we decided to use a light sensor on it, because if it was at a table edge, then you can just turn on the spot rather than going all the way around it, which would make it fall off. After building the robot, we had a couple of structural errors with it. Most of the joints were loose, and the brick was laying at the back, so it was weighing more on the back axles, and we couldn't use the differential pilot to turn 180 degrees because it was turning a lot slower, a lot faster, and it wasn't just going properly. So we've done a couple of improvements to it. We've fixed L-shapes bricks on it, so it's a lot more stable, and technically if you drop it now you shouldn't break. But
should we try that?
No. And I also fixed a couple more strong legs onto it and L-shapes here, so it's a lot more stable now.
We originally started by writing our program, the logic on paper, sort of a pseudocode, sort of based behaviour. Like we originally thought, how will the robot avoid objects? The sort of idea we had with it move forwards until the ultrasonic sensor detects an object that is too close. It will then turn the ultrasonic sensor left and right, and then find the side of no objects, and then have the differential pilot turn the whole robot to that angle. We originally created this whole program sort of in one class just to test the logic, and after we saw that our sort of behaviour was working, that specific action was working, we converted it into behaviours, and then this allowed us to add other new actions, sort of the light sensor and any other things we want to add. Now we can easily add on top of the program with everything else. The driver, it is considered to be the sort of the brain of the robot. It creates objects and variables. It also sets the initial values for the objects, such as the light sensor and the motor. It also creates all the behaviours and places them into an array based on priority. It creates an arbitrator which controls the behaviours via the array. With the priorities of our program, we have our trundle, which is the most important behaviour. Our trundle continuously will check the light level underneath the light sensor, and and it will travel forward until the value goes above a certain distance, which will then sort of detect that it's gone off an edge, or either the robot's tipped over and hit something, and then it'll rotate around to avoid the edges of the table, and then we'll carry on going forwards until the same sort of thing happens again. Our crucial behaviour is our backup behaviour. The logic behind our backup behaviour is it will keep moving forward. The trundle will keep moving forward until the ultrasonic sensor detects a value. Once it's detected a value within, I think we've set it as around 20 centimeters, it will take control, and the motor B will then turn the robot 90 degrees anti-clockwise, check that side, then 180 to go all the way to the other side, because our original position's in the middle, and then go back to 90 in the center, just so it can then start again. It will then read the values on both the left and the right side. It will then choose the opposite side to the minimum distance, and then the differential pilot will turn the robot into the direction which returns the highest sort of distance. And then the trundle will obviously take control again and carry on and repeat the process.
So, looking back at the entire process, we came up with a couple of things that we thought we could improve for the next time, and also just evaluating the entire process as a whole. So firstly, the most intricate part we found wasn't necessarily the programming of the robot, but rather what did we want the robot to do. So what exactly did we want the robot to do, how did we want it to behave, and also when it was doing something, was it doing the right thing? Especially, we found that especially difficult with the sound sensor, because as we all know, the sound sensor can be a bit unreliable. So that was the first point, what do we want the robot to do? Not always that clear. The second point, the practical function, so intelligence, movements. We've all been going through that, how randomly generated numbers can make the robot seem intelligent. So we took advantage of that as well. And also the placement of the sensors. We gave that a whole lot of thought.
Yeah,
Yes, as that's mentioned, because as he said, we wanted to mimic the animal behavior. We wanted it to be able to turn its head rather than having to turn the entire body each time. Thirdly, the environmental distractions. So, just because a robot works in some conditions, in some environments, does not mean that it works in every environment. So, for example, it works on a table, doesn't work on the carpet. And yeah, lastly, the identification of requirements and problems. So again, when it was doing something wrong, what exactly was it that went wrong with the robot? And in conclusion, we thought that was the most extensive part, the actual understanding of the behaviors, not just the programming and the functionality, but what exactly is happening.
Just get something like this.
Simple. No?
Let's see if I can try and get and they'll just go to the side, and they'll just carry on, and it won't fall. It should theoretically not fall off this table.
Oops.
Yep.
Still looking around.
Still look around. It should turn left now. Yep.